Hello everyone. Thank you very much for joining me in my presentation of my proposal work for my PhD, Quantitative and Qualitative Investigations into Trusted Execution Environments. The motivation for my work is relatively easy to understand. In modern times, it's become very important for third parties, such as AWS or Microsoft Azure, to be able to perform third-party analysis over various private records, such as in the smart grid setting, social network setting, etc. And this is relatively well supported in high-performance computation over plain text data. However, there are situations where the data may contain private information that cannot be safely put in the public domain, such as health data, banking data, etc. For this type of a situation, we need to develop techniques that can perform efficient aggregation or data analysis over data, but maintain the privacy and security of the data being analyzed. The importance of solving this problem has not been lost on major industry organizations such as Facebook and Sony, who have called for proposals to develop techniques for secure aggregation. In fact, Google has even adopted secure aggregation in their Secure Federated Learning Framework, which demonstrates the importance of this problem in real-world settings. However, even though it might seem like we can apply existing cryptographic techniques such as fully homomorphic encryption or secure multi-party computation, etc. to this problem, if we do so, this often incurs huge overheads that prevent this solution from being practically deployable in the wild. To solve it, however, trusted hardware, specifically trusted execution environments, offer us a promising approach if used appropriately. A notable technique for solving this problem is private stream aggregation, or PSA. With this cryptographic scheme, a user can independently encrypt their data and send it to an aggregator to be aggregated, such that the final plain text aggregation result is learned by the aggregator. Importantly, the individual data of users cannot be inferred by the aggregator. PSA is often used because it's generally superior to other techniques due to its low overhead, single round of communication, and asynchronicity. However, even though it's a powerful technique, it's limited to simple aggregation such as sum, average, etc., which makes it ill-suited to some more complex problems. Another newer technique to solve this problem would be to use trusted hardware, specifically a trusted execution environment, or TEE. Briefly, a TEE is a set of new CPU instructions that can be used to create an enclave within a computer. Code and data within this enclave is guaranteed to be protected from a process running at a higher privilege level, such as an operating system, from being able to peek in and spy on that code and perhaps learn someone's private or sensitive data that is sent into the enclave to be computed over. Importantly, this enclave can be attested on a remote platform to be running properly. So a user could perhaps communicate with an aggregator to run this attestation protocol to verify that if they're running a TEE, they can send their data with full confidence that the TEE is running correctly and the aggregator won't be able to spy on their code or data. There's not enough time to discuss the full details of what working with a TEE fully entails, but if you're going to use one, you have to split your program into two parts, an untrusted part and a trusted part. In the untrusted part, everything is essentially as normal, but you can send data that is perhaps encrypted into the trusted part to be decrypted and computed over such that you can return the plain text final result back to the untrusted part. Although we have these two really interesting techniques, PSA and TEEs, we don't have a really good understanding of how to use them together to perhaps get even better performance than using them on their own in isolation. Many protocols have components that might seem better suited for either TEEs or pure cryptography, and we'd like to have a better understanding of how we can combine these techniques to get the best of both worlds. Currently, there's no study that provides a quantitative or qualitative suggestion for how to combine TEEs with standard crypto primitives like PSA, and that's what my proposal hopes to accomplish. I've seen in my own prior work that It seems that there are scenarios where combining both these techniques offers superior performance than using them on their own. And as a result, I propose to design a framework that we can use to quantify the potential for performance improvement by combining the techniques, and also provide qualitative advice on how to best combine the techniques to achieve optimal performance. In summary, my proposal has 3 parts: to develop a quantitative framework, to develop a qualitative framework, and then hopefully use both of these to formulate a case study where we can use the frameworks to improve the performance of an existing protocol. Among computer security professionals, currently there's a lot of unanswered questions regarding the performance implications of applying TEEs to solve common problems within the secure aggregation and data science space. TEEs often interact with the computing platform in complex ways that make it very difficult to quantify the potential for performance improvement or degradation compared to other pure cryptography techniques that don't rely on trusted hardware. In this type of a situation, pure cryptography would have to be augmented with advanced hardware like GPUs to be competitive with TEEs, and because of all these conflicting complex constraints, it's unknown whether the different costs and benefits associated with either technique would justify either setup. To solve this problem, I plan to develop a statistical model that will measure the potential for increase in or decrease in overhead for both the runtime and the throughput for either approach. I'll also develop a related model that will be able to predict which approach will offer the best performance based on the user's available resources. Importantly, both models will be able to determine the impact of combining both approaches in a hybrid model, and if using this type of hybrid approach will offer superior performance. Now, this is a hard problem to solve. It's very challenging to quantify the potential for performance gain or degradation based on the resource costs for a specific computing task, because the pipeline of operations to compute a learning algorithm are often dependent and complex based on the different technique you use, TEEs versus PSA. It's not clear at all how we could rigorously quantify which pipeline will be best for either domain based on what resources are available to a user. Another gap in the existing body of knowledge we'd like to fill is to better understand which types of computational tasks are better for TEEs or PSA. Recently, the high overhead from using pure cryptography has led to a growing interest in using TEEs to solve privacy-preserving computational problems. In fact, this has led to several types of computation that were previously thought to be intractable in the privacy-preserving computation space to become practical using trusted hardware. However, existing approaches are generally ad hoc and could be made better if there was a systematic way to identify which types of computing paradigms would be best suited for TEEs versus PSA. So we could look at a problem and break it down and build an algorithm from existing computing paradigms without having to reinvent the wheel every time. To expand the body of knowledge in this area, I plan to compare the performance of using either PSA or TEEs to compute different types of privacy-preserving computational tasks, and better learn which type of program logic is optimal for using either approach. Once this is done, we will be able to investigate how both of these techniques can be combined and interfaced together in the computational pipeline to develop new ideas for what's the best practices when combining different design patterns. Once this is done, we can build an algorithm to assist developers with assigning different computational tasks to different technique workflows to improve performance. Here we will encounter many similar challenges to those we will face when developing a quantitative framework. Again, it's hard to know at a glance which tasks are better suited for TEEs versus PSA. This is because TEEs have their own set of complex performance constraints, including overhead due to context switching between the untrusted space and the secure space, also known as the enclave. Also, once inside the enclave, there's a lack of sophisticated parallel computing opportunities, and the enclave can only fit a fixed size of code and data. Only a rigorous study will allow us to understand which computing paradigms are best for either domain. Thanks, and this concludes the talk.